Yeah, good evening. Thank you, and welcome. So nice to see you. Thank you for joining. Yeah, good evening, Komal. So let us start the discussion where we'll go through normal distribution and other distributions, and also we'll start the discussion related to sampling and distribution. Now this just to summarize, if we take the discussion what we had in the previous session related to normal distribution. So a few points or summary of the discussions related to normal distribution. One is its probability density function 1 by sigma root 2 pi exponential x minus mu whole square by 2 sigma square, where it takes all the values minus infinity to plus infinity. Right? That is the first one. So where when we apply normal distribution, for example, if P of x1 less than or equal to x less than or equal to x2 for some values of x1 and x2, then what we do is we convert them into standard normal distribution. So why to do it? To handle that integration and to use tables. That is the simple reason for it. So standard normal distribution means we'll convert into z scores, z x minus mu by sigma. Then what happens is this becomes p of z1 less than or equal to z less than or equal to z2. So where here mu we know and sigma we know. So we convert each x1 into corresponding z. So once it is done, then it is simply f of upper limit, that is z one into z2. Similarly, z1. So this is the process where whenever we want to apply normal distribution. Third one is when we think some properties which we can use when we compute 1 minus f of z. Right? And another one is whenever we see something like this, then it is 1 minus f of z1. Like say that is some properties. So this is discussed in the previous session. Very simple, but only as discussed many times. So here we take the help of normal distribution tables. Okay. Now, just an example. Suppose if you take this data given x as it is. So it is having mu x, that is mean of this data is 3, standard deviation is 1.41. So suppose if we convert this in terms of z, that is standard normal distribution, right? That is suppose take this. So we have to find mean variance and do these computations, that transformation what we call as. So x minus mu x by sigma x, then these are the transformed values we are getting. And if we find mean of this transformed values, what we are getting is 0 and standard deviation is 1. It means, so why we have to, it's very simple, right? Why we have to standardize means everything falls into uniform way, right? That is whatever the values that we get here, right? So finally, once we go for the transformation, it fits into a distribution whose mean is same, that is 0, and standard deviation is 1. That is the advantage. So why we have to go for? So I hope maybe by this time you might have seen this as a part of your data pre-processing. I hope whether you have done it or not. This transformation, we might have done it standardization of the data, right? Suppose, I don't know whether you completed regression discussions, something one in machine learning kind of discussions. Suppose if the data is coming like this, X1 and X2, where X1 is like this. And X2 is something like this. Maybe it is years of experience, this is the salary and like that, right? Now, if you see here, when we work with this data to find a relation, so here it is in a different scale, different scale in sense here it is large in numbers, it is smaller in numbers. There is a possibility that it will try to dominate the situation, right? So that is where what we do is we'll push everything. We'll use this. Suppose if you convert it in terms of G-scores, all the values falls into uh, this scenario where mean becomes 0, standard deviation becomes 1. So doing the same, mu equal to 0, sigma equal to 1. That means now all are in the same scale, so that it is good to go ahead with uh, regression or whatever. I hope you might have done this
Yes, sir.
standardization. Yeah.
Just
The
service
reason
is
is
given in
this.
the regression.
That's right. Yeah, very good. Yes. So that is why we have to do it. So putting it everything into same scale. Okay. So where many strategies, most popular one is G-scores. That is this. Okay. So this is, I think, I hope this is very clear how to use it, how to read it, and what is the confusion comes with it. So most, so minus infinity to z is this here. Right? If you see any other table where all the values are below 0.5 means, if you observe closely, it is 0 to z means they consider only this part. That is one.
Sir, I have a question, sir. Can you go to the last slide, sir, once? So the last column is the standardized value of x, which we will be using in the model. That's what you're saying, right, sir?
This is.
This one. What is z minus mu z squared? Last column.
That maybe you can use to find variance, etc. It's minus mu whole square by n minus sigma, etc. To find variance, right? It is.
Okay, 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 okay,
For us, this is the display. Just
okay, okay,
X
okay,
and Z.
okay, sir.
Sir,
There
I
actually
understood Z. Can you tell again what is mu Z?
mean of Z. That's it.
अच्छा,
Mu
zero.
stands for
समझ
mean.
गया. Okay.
Actually, this last column is not required here. This column is required to find sigma x. But this they have done to find this also, not required means. So if you recollect how we compute this x minus mu x or x minus mu whole square by x, right? So that's why they calculated this to find sigma of z. I think the examples I hope you are comfortable in doing problems involving normal distribution. Now, there is something I think some of our friends asked earlier. Suppose n equal to 1000. N equal to 1000. We want to find P of x greater than or equal to 500, 520, where P is given some 0.3. And this follows binomial distribution. I hope. So actually it is a binomial distribution problem where n equal to 1000, P x greater than or P is 0.3, x greater than or equal to 520. Now we understood that here what we need to do is P of 520 plus P of 521 plus P of, and so on up to P of 1000, right? Otherwise, 1 minus that also we can do it. Now, how complex this computation is? I hope. Right? This is a computationally complex. If it's when now, suppose if it is normal distribution, you see any complexity involved in computations, if it is normal. Any answer for this? Suppose this is P of X greater than or equal to 520, right? So if it is normal, do you see any complexity in doing computations? Simply write something like zeta greater than or equal to some value 0.5, then 1 minus like this only, right? If it is 520 or 100 or 1000, any value here doesn't matter, right? I hope.
Could you repeat the last statement, sir?
Now here P of X greater than or equal to 520, P of X greater than or equal to 520. Suppose consider binomial distribution. We know how to do it, but these many probabilities we have to find, right? NCXP power XP with 520, 521 like this. We have to do it for all these till 1000 and sum up. Right? Now, suppose this, assume that the problem is given like this, where this follows normal distribution. Now you see any difficulty in computations here?
No, just
No, right?
f of limits. That's it.
Where is it, right?
Yeah.
So that is what here normal approximation to binomial. So where we'll try to, actually it is normal distribution. Now what we do is we try to use normal distribution in place of binomial distribution. It's someone called the same doubt expressed by someone yesterday, right? This is answer. So how to do it, right? Very
Sir,
simple.
one small doubt, sir. I mean, here one is more of on the discrete side and normal is more of on the continuous side, right? So,
Yes.
and
Yes.
I would assume we have, I mean, this is when you say complexity in computation, is this manual or because in the end, this is all done via a program?
Even then also, right? Then also comparing with this, suppose take computational aspect of this as well as this. Right? So even if you program it, also here it has to compute all those things, right? Whereas here it doesn't matter. Suppose if 1 lakh here, n is 1 lakh, right? And this is 5,200, 5,200. You see, in case of a normal distribution, it's a very simple computation, right? Just Z value, that's it. I hope you are able to figure out the difference. If 520 or 5,200 doesn't, is not a big problem. Simply Z value will find 1 minus F of, that's it. Whereas here, you see how much computations we need to go for, right? And that too, in these computations, we have to do this NCX, P power X, all those things, right?
Okay, okay.
I hope.
Yeah.
That is where we'll always use something called approximation. Very simple, I mentioned earlier, right? So initial stages, we are confined to, this is called as a discrete, this is called as a discrete, right? This is a discrete, right? Now simply I make it as a continuous, right? This is a continuous. Or continuous can be discretized. That is if you will have some discussion in your machine learning discussions as a part of pre-processing. Right. So initially we'll have some clear differentiation between this is discrete, this is kind of later depending on our requirement, even continuous will convert into discrete. Discrete can be approximated with continuous and so on. So now in this aspect, how we do it? Next question is very simple. Very simple. Now here z equal to x minus mu by sigma, right? Now the approximation is we assume that it follows binomial, actually binomial, and we assume that it follows normal. Then it becomes x minus mean of normal distribution, binomial distribution is NP. And this is NPQ under root. That's it. So generally, when we can go for not whenever it is computationally complex, they found a rule like the NP greater than or equal to 15, NQ greater than or equal to 15. Better don't jump into this complex computations. Instead, you can go for approximations. So this is 15 is the boundary. NP, NQ, not NPQ. See for any problem.
Sir, could you please repeat that NP and NQ repeat limits, how it is coming once again?
This is, I think, the research. They observed it. Not that don't take the advantage of this every time. That is what better go for. The reason is the research evidence here. If in this case, if you go for you won't see much difference between. That means what does it they mean is suppose if you do computations by taking this binomial as it is, if you take normal instead of binomial distribution, then there won't be much difference between the output. Very less difference, very minute. So this they observed only when these situations are met. That is like a research observations kind of thing. That's why they proposed it. So maybe if it fails to do, then you may see some difference between the output when we follow original distribution and normal distribution. Yeah. Yes. This is.
Okay, thank you, sir.
Yeah. That is the actual research, the observation, what we can call as. Right? Just these examples to see whether it is applicable or not. So N is given, P is given, whether we can apply normal for this binomial, where NP and Q are the base rate. NP is 9, but NQ is 16. What we require is 15. Therefore, so normal distribution cannot be used. That's the only thing. Let us see with an example how to do it. 31% of seniors in a certain high school plan to attend college. If 50 students are randomly selected, find the probability that less than 40 students plan to attend college. By normal, approximately clearly mentioned, otherwise we'll check it. So here n equal to 50, right? Where is that one? N equal to 50 and 31% is the probability. So NP is 0.31, so 15.5. So 1 minus P is Q. So NQ is 34.5. That means yes, good to go with normal approximation. You see here actually, if you see the problem, is it a discrete problem, continuous problem?
This is a discrete.
Discrete, right? So, but we are solving it by continuous. That's why. So there is no difference between discrete and continuous later. That is what I mentioned sometime. So now once it is clear, very simple. What is that they are asking us to find? Greater than 14. Less than 14. There is one more point here we discuss. Less than 14 means this, right? P of X less than 14, right? Less than 14, right? So because it's a continuous, generally people prefers to go for the, because it is continuous. So here instead of this, we can take it as 13.5. Is it justified? Actually, this is what we require. Instead, if I take this, is it justified or any comment on this?
Yeah, it is justified because anything less than 14 will start from 13 only.
Yeah, generally they follow it. So it is like some correct 13.5 down the line, everything is less than 14%. So suppose 13.6, 13.6 is a 14 actually, right? 13.7 is a 14, 13.8 is a 14, 13 like this. Okay. So like this. So this is very
Could you
important.
explain the correction for continuity? Why is this reduced? Why minus 0.5 is done from 14?
No, if you see, there's a actually it's a continuous, right? Suppose if you take 1 minute, I'll write like this. 1 minute. G2.
Sir, here less than 14 students means Z1, X1 we needs to supposed to take a 14. Greater than means 15 we needs to start instead of 13, right?
Less than 14, right? Actually, this is less than 14. Px less than 14, right?
Okay.
Now this is actually discrete wise less than 14 means 13. Now, if you see, it is a continuous case, right? 13 to 14, everything now. But if you see in reality, between 13, 31.1, 13.2, 13.3, 13.4, 13.5, 13.6, 13.7, 13 point like this. Suppose if you take 14 as it is, what happens, right? Now, if you see all these are nothing but 14 only, right? Equal to 14, right? You see, this is nothing but 14, right? This is nothing but 14. This is nothing but 14. Am I
As in
clear?
you rounded it to 14, no?
Yes, yes, that is the only difference. Yes, a small difference will be there. That's why even if you want to avoid, that is where they do this correction for continuity.
Was it done because we converted a discrete distribution into a continuous distribution?
Yeah, now this, it's just see this. Originally it is less than 14 means all these values comes. But if you see, if you round it off, 13.4 is 14 actually, but it's less than 14, right? That's why we ignore this. That's why less than, you can write as less than or equal to 13.4 or strictly less than 13.5. That's it.
But my question is, why did we do this in the first place? Why was 14 not used?
This is the reason, right? So here strictly 14, right? Strictly 14, right? If you follow as it is, that means we are considering all these values, right? All these values means 13 point, if you round it off, it is a 14, right? It is also 14. It is 14. It is 14. This is 13. This is 13.
So aren't we considering these values in Px less than 13.5?
This is the reason, right? So actually between 13 and 14, you'll have two halves where the first half contains, if you adjust it 13, second half contains 14, right? But here it is strictly 14 means better not to add this part. That is what they have done. Oh. Once it is okay, then very simple. Then converting this into Z, the regular process. So when here normal approximation, what we are doing, then yeah, it is. I'll copy here. So Z equal to X. Now rest of the things is as usual. X minus mu by sigma, X 13.5, mu 15.5, and sigma already think sigma is NPQ under root, right? NPQ 3.27. Plug in all this. The rest of the things are same.
So, sir,
So-
if the problem statement was find the probability that is less than or equal to 14.
No,
Then-
less than 14.
No,
Then
case,
then we can tell the answer.
so it will be px less than 14 if the
Yes,
problem
sir.
was phrased that way. Okay.
Yes,
clear.
yes.
Sir, can we consider Px of less than 13?
Less than.
Yeah, as it is, we know it is a discrete problem if it, even though we are using continuous normal distribution, it is better to use 13, right? There is no person in between
No,
13
actually,
point.
if you 13.7, 13 point, all are nothing but 13 only. No?
Yes, but the area calculation, it will affect, right?
That's why less difference, very less difference. But why I took this is 1 minute. Why I took this and focusing on this is, suppose this problem is given where it is asked us to find exactly 17. Then how we do? Exactly 14, not less than, not greater. How we do? Any guess on this? I hope question is clear. Find the probability that exactly 14 students plan to attend college by using this normal approximation.
13.5 to 14.5 would be.
Because normal distribution requires interval, right?
Yeah.
Inequality required, right? Now that makes sense, right? Here, this is nothing but TF. Now you can tell what is the interval. We can, it is up to you, strictly greater than, strictly less than, like. Suppose if I take strictly 14.5, right? Here. So, is it make sense?
Or, sir, I
If-
can test the boundaries, right? 13.9 and 14.1.
What is the sin done by the 13.8? Simply what we are doing is, actually, if you see maybe histogram kind of thing, this is what we want 14. Then what we do is this also falls under this, right? That is what we are trying to do here. 13.5 if you adjust, right? 13 point here if you see 13.5, 13.6, 13 point, just roughly we are taking some values, 13.8, 13, sorry, 5, 6, 7, 8, 9, 14, 14.1. If you see, if you round off how much, this is 14, this is 14, this is 14, this is 14, this like this, all we are taking. Now you can see, actually discrete, we are converting it to continuous. I hope it is convinced now, at least.
So, sir, had it been an equal to sign, we would have considered on till 14 actually, right? If there would have been a less than equal to students 14, then we would have considered 14 only. So it's because in the Z score table, we will not be able to find out less than, and you have to
No, jet table
really
is not a
point.
problem. No. Jet table is not a problem here. This, as you mentioned, because less than, then we consider 13. Suppose less than or equal to. That means 14 in ND is also considered. No need to adjust it, right? No need to do any
Correct.
correction.
Correct. No, so my question was more like, because we are referring to a Z score table, right, where you can only find till that certain point. So that is always less than or equal to is always there in that
No.
to be able to find the Z
No.
score.
What I mean to say is, first, don't think of the next. Actually, first, once we figure out, then only we'll take the help of computations, right?
Okay.
That's why, not because of that we have to do it. No. Let us do it, then taking the computation part, that is where we'll get into distribution tables, right?
Okay.
That is actually the correct way, not because it is available, I do it.
Achha. Okay.
I hope this point is clear, right?
Could you explain the point again, sir, where it is x less than equal to 14?
And also, even we can extend 1 minute, remove some of these points. All the unnecessary portions entry. Even 14 also some correction actually we can do it. Originally, if you ask me, yes, not 14. 14 also you can correct, modify it with corrections. Just a minute. Just a minute. I'll write here. P of x less than 14. Then I hope it is clear. We can or we take as less than 13.5. Suppose as mentioned by our friend, less than or equal to 14, then what is your comment on this? Whether we need to take this as it is or any correction you suggest?
That's correct, sir.
And for any response. Same as it is or any correction?
It should be 14.5.
Right.
Yeah,
Yes.
strictly or equal to means 14.4. Right? 14.1 is nothing but 14. 14.2 is nothing but 14. And third one is if you take x equal to 14, then it is P of 13.5 less than x less than something like this. Even if by mistake if you put equal to also that doesn't make it because it's approximation, right? Approximation gives a more small error, doesn't make much difference. It's not a sin actually. It is not that big sin to be avoided. I hope this is clear, right? Is it clear to proceed further?
Sir, one small question. So 0.279, how will derive it for this one value?
Which one? From tables. I don't take this what kind of table they have taken. Just refer minus 0. Don't follow this. Just go back to our. Maybe I'll write here. Actually, it should come next. P
So-
of x less than 13.5, which
Okay.
is nothing but P of z less than minus 0.61. Now, if you observe less than, we won't do any modification, right? As it is minus 0.61. F of minus z, if you want, we can make it as 1 minus f of z. Then 1 minus f of, just take the value from the table for 0.61. Right, I hope. 61 from the table. 0.6. 0.6 and 1. This is the value, right? 0.6 here, 1 here, 0.729. 0.729.
So in
Then
exam,
we
how
get-
can I find, because table we don't have, right? How can we derive this answer?
Without table, you can't do, even I can't do.
Oh,
You
okay.
suppose if you think I am so knowledgeable comparing with you, suppose if you assume, even then I can't do it.
Sir, I think it will be given in the question paper if I'm not wrong.
Yes. If
Okay.
not given, don't worry. Just close with this saying that table is, you need not worry, you need not ask anyone. As the table is not provided, so this is not completed. That's it. You need not ask anyone. So I need this. Don't worry about it. Right? Generally, we give. You will give. The question paper comes with the table. If not, don't worry. Just do till this part and comment there. They will take care.
Till which part?
The last part. This till this we can do it. Right? Table is not required. Right?
Okay, sir.
That. No one can do it without tables. Right? That's no worries. If anyone, let me know. We'll recommend them for some award. Well, it needs lots of math computations, special functions, complex integrations. Okay, this is another example in the same lines. So N40, PQ, then applicability. Here, even though it is mentioned as normal approximation, always better to validate it. Is it worth going or not? Right? Even though they mention it as, right? So this is the condition, right? Here at most 20. Right? You see this statement clearly. At most 20 means what for us?
Equal to 20.
than or
Less than
equal
equal
to.
to,
Less than.
less than or equal to 20.
So which is modified as less than or equal to
20.4.
20.4 actually, right?
Yeah.
I mentioned no, just one digit from here to there doesn't make any difference. Don't think it as a mistake kind of thing. It doesn't make much difference, right? Strictly speaking, this is correct. Otherwise, what they mentioned is also almost correct. But if you truly speaking, it should be something like this. I hope very simple. Then rest of the things are same, right? X conversion into Z, then using tables and plot. Okay. Now, actually, mostly we won't use, but still same is applicable for Python. Same is applicable for Python. But rarely we use, but still it allows. Same way, similar to this, Z equal to X minus mu by sigma. Sigma means lambda.
Standard
That's right. Same. If it is a Poisson distribution, rarely we use, I never saw it, but theoretically it is accepted to go for by normal approximation, even when it is following Poisson distribution. Now, another, just to get ourselves familiarized with names, another distribution which is very important for us when we use it is chi-square distribution. So don't worry about lengthy expressions. Don't worry. Just try to figure out that there is something called as chi-square distribution, where whose PDF is given by this. This is nothing but some complicated integral called as gamma function. It's again an integral actually. It's a complex integral. So forget about it. There is something called as a chi-square distribution, and whose graph looks like this. That's the only thing we require. Remind things. Don't worry about the expressions part. Most important thing when we talk about chi-square distribution is the last sentence. K is the parameter of distribution known as degrees of freedom. That means when we talk about chi-square distribution, so one is how it looks like. It is not like a bell curve. If you see here, always it starts from 0 to positive quadrant only. That is one aspect. And second aspect, it comes with the degrees of freedom. I hope you recollect the discussion we had when we talk about degrees of freedom, right? At the beginning, somewhere we discussed this. So that is one. So again, here we are not going to do any integration. Just like our normal distribution, we are going to use tables related to chi-square distribution. That comes later, maybe module 9 or 10 something. This is the graph actually. It is not bell curve if you see clearly. This is from 0 to X. This is a table value we get. So maybe we'll have a discussion when we go further when we use chi-square distribution. Just we are trying to understand that there is another distribution which is related to continuous variable, which is chi-square distribution. And one more is T distribution.
Sir, are chi-square and T distribution in the syllabus for midterm?
Nothing is there to ask actually, right? Actually, just introduction, like say there are some distributions. Actually, we use this when we go for testing of hypothesis in the next module. Okay, yeah, nothing this to ask for examination. So another distribution is T distribution. So any observation here? The graph is given here. The graph is this. So here the same discussion. Some big function is there, which is its PDF. Don't worry about this. I think complicated expression for you. This is a gamma function. Gamma function is another integral actually. It is. Don't worry about all the things. We are going to use T distribution. The most important thing is the graph of it. Now you can see this red, blue. These are all graphs of T distribution, where this is our normal distribution. I think I'm expecting any questions after seeing this diagrams.
Their upper range is
Peak point.
lower than standard deviation, and they have tails, longer tails.
Okay, yeah, correct. Correct. Any other? Almost it looks same, right? Actually, it is also bell curved. It is also almost same properties. It is also bell curved.
So
Only
more
different.
points nearing to zero.
Okay. Actually, I'll suppose if you say this, okay, assume that is a bell curve. Yes.
So the data is more spread out, is it like more
Mhm. Yes,
smoothly
yes.
spread out?
So I don't know whether you played in beaches with the building houses like this with sand. I don't know whether you played or your kids played. Have you seen like generally at least. But I was played with this when you go to beaches with sand. We play when we build houses like this. No,
Yes, sir.
Yes.
right? It's like that. Now, if you see, suppose if you remove some particles, some part of this, then what happens? The shape gets disturbed, right? The shape gets disturbed, right? It will collapses, right? It comes down like this. It is so delicate when we build this with sand and beach, right? I hope,
Yes, it's loosely coupled.
right? Loosely. Whereas if you take this bigger ones, no, right? That means actually the generalized thing is our Z distribution, the normal distribution, where it will have some delicacy up to some points. That is where it says that it follows T distribution. That's why it looks like almost the T distribution curves are nothing but shades of normal distribution, right? Standard normal distribution, normal distribution. So here the thing is, because here it is observed that the sample size is less than 30, sample size is less than 30, then it flattens, like what I mentioned, right? So it removes something, it flattens, right? So it is more delicate. If it is greater than or equal to 30, there won't be much change. That's where it follows normal distribution. This is T distribution. I think we'll use it. We'll have more discussion. That means it is so delicate, right? Delicate than degrees of freedom comes for discussion. Whereas this is a rock solid, nothing happens 30, 40, 50, nothing happens. That's why it's a normal distribution always. Normal distribution when sample size less than 30 is more delicate, which depends on the sample size. That means the degrees of freedom, where it is T distribution. So as of now, that is the summary of T distribution.
So the variance or the standard deviation of T distribution will be more because it's more spread out curve.
Yes.
Okay, okay.
That too depends on the sample size. The how much sand you take, that it
Right.
flattens, right? That's it. That's so
Right. But
delicate.
for the same sample size,
Ah.
the normal distribution will have a smaller sigma square and the T distribution will have a bigger sigma square.
No, for same sample size means what is your sample size? Suppose it is greater than 30, undoubtedly it is rock solid. That is normal distribution.
Okay. So if
So
it is
it becomes delicate less than 30.
okay.
That's why you take a bigger house built by like a hill kind of thing. Other one is a similar house built with sand in a beach, which is so delicate. If you remove something, it goes towards flattening, right? So the delicacy is nothing but degrees of freedom. How much sand you take is there. Here, what is the degrees of freedom? That is sample size.
Okay.
So I bet you won't see this kind of difference anywhere. This kind of explanation, I bet. So correlating this both with this, I think. Now other one is, I think the formulas and I will see it. Other one is F distribution, is another distribution, which is a complex expression. So another distribution, which is also continuous distribution. So I think we'll use it when we go for next topic. Okay. That means the summary here is there is something called as sampling distributions. So, no, sorry, not sampling, probability distributions. Sorry, not word use, probability distributions. Means I hope now you got the idea, like probability distributions, nothing but some patterns, right? Some patterns that the data follows containing probabilities, nothing but probability distributions. That for our understanding's sake, based on the nature, we divided them into discrete and continuous. And discrete, we discussed Bernoulli, binomial,
Poisson.
Poisson. In case of continuous, normal, standard number, etc. And other one is chi-square, T distribution, F distribution. Many are there, gamma distribution, beta, many are there, but we are not into statistics. So these are the mostly used things are for us is normal, chi-square, T distribution, F distribution. So these mostly we use when we go with sampling distribution, testing of hypothesis or inferential statistics for us. That we'll discuss when we go for the relevant module. Right. I hope things are clear. Any doubt, any? So confident.
Yes, sir.
Next, we'll take the discussion where sampling is what we call as. So I think, and in our experience, we are like a matured experience. The sampling is a technique which we follow regularly, right? I think you can give some examples where sampling is used, why it is used. I think I want to hear from you on instead of me telling all this. What I learned from textbooks.
So if some waveform is there, if we want to take some number, so we might do the sampling to that waveform to get some number. I mean, some discrete number. So that is one way for digital
Yeah.
communication.
You are educated. Suppose if you ask your mother, she also do sampling, right?
Rice cooking.
Right? You are so educated, you know signals, digital, etc. I think your mummy is also doing sampling regularly, right?
by taking some rice,
Yes, sir.
whether it is cooked or not.
Okay, good.
Right. So that is actually sample. So why we need it? Why we need it? Not only this, the Dr. C guy comes at home and takes samples, right? Blood samples, urine samples, right? And when we go to a sweet shop, he will give, sir, naya sweet jara taste kijiye. Like he will give a small piece, right? All these are nothing but samplings, right? Sampling techniques only, right? Sampling.
Mm.
Right? So why we need this?
If if entire system is evaluation is very difficult, so we'll take a sample and evaluate that one.
To get some
Regularly we
idea
use
about it.
Yeah, regularly we use, and academically in our class 2 we did the chemistry experiments, lab experiments, organic, physical chemistry, all those things, nothing but involving sampling. So here we'll use some terms. The total objects under consideration is called as a population. Right. So here one is not required, sometimes not possible to look into all the objects to understand it, right? So we want to understand. So that's why not possible, sometimes not required, time consuming, more efforts. To avoid this, what we do is we'll take a part of it. A part of it we'll take out. And we do the analysis on this. We do analysis on this, right? Now, based on the analysis, what we do is we'll try to understand the entire objects, all the objects. That is what you say blood. Now, if you take entire population, means the entire blood in the body, right? So to study blood picture, do you think that we have to take out the entire blood from the body, keep it in a bucket, do the analysis, then again inject? No, right? That's not possible. So that is where blood samples they collect, right? Blood samples. Then they do all the testing on this. Then finally the report what we get is not with respect to this. They'll do it for this, right? Whatever the report we get, it talks about the complete blood picture, right? Blood profile is what I think we can use the term, right? So to understand this, what we are doing is we take a part of it, we'll do the analysis on this. From this, we'll try to do or understand this. This is what is called as sampling. Okay, I hope. That's why when the cooking is doing, mommy will take a small part and taste it, right? Then so you add salt, add something like this happens, right? That is right.
So to do some estimations for the entire population, depending on a single section or subsection.
Yes. Now, while doing so, it looks good, but do you think that we can rely it on completely or any? Hello, are you able to hear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. Here, I think my desktop disappeared. That's somebody, I don't know. That's why. Now, just imagine before taking curry for tasting, I think mummy follows some technique, right? Mummy or wife?
Both.
What they do? Before taking, what they do?
They will just stir it so that like it will they won't get the only upper layer part of it kind of.
They'll take one drop from that and taste it.
Now,
To
before
check for
taking,
salt
no,
content.
no. Before taking, they stir it, right?
They
Stir it.
stir it so that like
What
they
is,
won't
why
get only the
why
top
to stir
layer.
it? Why to stir it?
Otherwise, you
So-
will get only
Randomize
the
it.
top layer.
Distribute
To randomize it.
correctly.
actually sampling
Make sure
has
Instead
that
of the
the
to
make sure
Instead
that
of the large
population
part
is
of the
homogeneous. Homogeneous.
Yes.
You see, simple things now. When we work with data, the same things are required. That is one. That is to make population more effective. We have to make sure that population is homogeneous, right? That is one. So One is sampling is very good. Now you might have seen these all exit polls, opinion polls, surveys, whatever they are using. You might have, whether you follow the exit polls, opinion polls during the election season, they talk about what is your sampling, sample size also they discuss, some people they talk about, right? So it is a very good technique, but we have to be very careful with some aspects. One is homogeneity, right? Homogeneous. We have to see that the population is homogeneous. That is what mummy do, stir it before taking a part of it and taste. Second one. Any other aspect. So what I'm saying is, what are the things we have to take care so that our sampling gives good understanding of the population?
So it should be representative of the population. What are the properties population has, sampling should have.
That is what I
Quantity,
think steric,
quantity.
homogeneous, right? Quantity,
Okay.
yeah, that is sample size. I use the word, right? Means there should be some proportion. Otherwise, suppose if we are having 1 lakh objects, I'll take only 2 and do it. Doesn't make sense, right? Oh. So some proportion, that is somebody mentioned, sample size also makes it. Anything?
We should
Or
check. We should
frequent
check
iterations.
internally, periodically. So I mean, the interval should be there.
That is estimation. That comes next. Actually, now we are getting into what are the things we have to take care so that our sampling gives better understanding.
Technique used to sample.
Yeah, appropriate. Maybe statistical technique or technique. So what is your objective and what is the technique that we are using? That also makes difference. For this, in a funniest way, I'll give an example. Right? Funniest way, so your daughter, small kid came with you when you went to buy the vegetables. Right? So she observed, suppose you are buying tomatoes. So how we buy tomatoes? Right? We'll take them in hand and we'll see it and put it, right? Tomorrow you send her to buy the lady fingers. If she does the same thing, whether you'll get good lady fingers. I hope.
Probability is less.
No.
We use some tick technique, right? I think those. Right now that how you buy tomatoes doesn't work for lady fingers. So there, I think ladies use the technique that at the end they will press it. They will get a tick sound. They will take it. Otherwise, they will throw it. Right. What I mean to say, that is important, right? Suppose if your daughter comes and with the lady finger selected in the same way, no, it is not a good selection, right? So appropriate technique is whether you want to use a mean or median or mode. What is the technique, statistical technique or tool that you are selecting to understand the population? So that is what is meant by appropriate technique. So these are so here why sampling, to how to make the sampling more clear. It is more helpful for us to understand the population and all. Next is, what are the types of sampling? So in general, there are many types we won't get into. We'll look for the sampling techniques, which are very important, useful for us when we work with data. One is, I think many times our friends mentioned random sampling. Right? I think what is meant by random sampling?
We have to pick up
Randomly select
class.
some items out of population.
Randomly select. That means every element is having equal chance of being included, right? There is no bias, right? That is what is meant. Right? There is another sampling which is very prominent, popular when you work with the data, that is stratified. If you are already having that experience of implementing in Python, then you might have seen this term used and this term used sometimes. So what is the stratified sampling? So in general, general application, if you take, suppose in generic, we want to study the economic improvement or status of people in India. This is what. Now the Indian, this is the population, all Indians, right? This. Now, can I go for random sampling from this?
No, then chances of getting same kind of economic people will be there.
Because
You may not for all economic classes sample.
here you will have two things. One is you people will be there, all your people, right? And apart from you, one more dangerous sector will be there, that is politicians. Because their wealth is more, and you are also, but you are genuinely, but there. Now, if you take this population, then is it going to give exact understanding? No, right? We have to divide it, right? Our section is divided into various classes based on economy, right? So like general terms, what we use. So lower middle class, upper middle class, like this, right? So here the population is not homogeneous, not uniform, not homogeneous. Right? So then random sampling is not. What is the wise way of doing it? Divide it now. This is a uniform, right? This is a uniform group. This is a uniform group. This is a. Now select from this, select from this, right? I hope that is what is called as stratified sampling. If the population is not homogeneous, divide them into stratas where each strata is homogeneous and see that every strata is having representation in the sample. Then sampling gives good understanding of the population. Right? So that's why this is important. Why this is important, we'll see. Now we'll take our context. So this is the brief understanding of sampling. Now coming to our context. So when we work with data, where we use sampling? That is the first question, where we use. In what way it is relevant for me as I am going to work with data. When we work with the data, I hope by this time you understood, we divide data into two parts. One is testing, training and testing, right?
Yes.
Right. I hope you by this time you already start where, right? 80, 20, some numbers, right? Or 75, 20, some no standard rule. So now if you see here, the population, this is the population. Population is data. Right? Here for us, data is population. Now from this, we are having two things. One is, this is the sample one. This is sample two. This sample consisting of 30% of the data from this, 70% of the data here. So where this is called as in the machine learning kind of scenario, training is for testing. Now I think this is where sampling is used, right? So, right. So here, what kind of sampling? General random sampling. So randomly we select records into this sample and this sample. So this is one use case for us. Always, every time we use sampling, that is when we work with data. Right? That's why this is relevant for us. Okay. For a place to. So any other? Now, while doing so, this is random sampling, right? Random sampling is general, but sometimes stratified we use. Any guess on this where the stratified sampling is used? Why it is required there?
As you said, sir,
Preparing income tax slabs. the way you said, right?
Okay, okay. Particularly with respect to machine learning language, I hope by this time you had a classification. You understood what is meant by classification, right?
Regression cases.
Regression
Yeah.
and classification, supervision. In classification, particularly medical related records, if you take, suppose 1,000 records, if you take, in general, this comes with mostly 800 no disease, 200 yes disease, or vice versa. Do you think random sampling is good with respect to this?
No.
I hope, right? In general, medical records will be like this, or vice versa. 800 with yes disease, 200 with no disease. Suppose if we go with random sampling, what happens?
There
We
will
won't be
be
able to
80%.
we won't be able to uniformly represent the different
Population.
classes. That is,
Mm.
yeah.
But actually, you won't see any problem, right? No problem is visible. You won't get any error, syntax error kind of thing we see. No problem at all, right? Thing is, you are trying the model in this case where it is exposed to only mostly no disease instances, right?
It's just-
The training
Exactly.
is right? Training is more of no disease cases. Then what happens if you actually S disease case is not exposed, right? A
Right.
simple example is if the
Yeah,
doctor is if the doctor, suppose if you take a doctor, he is always a doctor who do the only prescription. That we go there and he will use that stethoscope and write something like right. So he is exposed to only that kind of scenario. Suppose suddenly any operation case comes, will he able to do it?
Definitely not.
That is because it is not his problem, right? He is mostly exposed to those kinds of scenarios, right? He is trying over it. Now, here also, with what I mean to say is, in these scenarios, if we won't do anything straight away, random sampling, if we go, nothing will happen. But we are trying the model over 800, there were no disease cases. Then when the new instance comes, it may fail to classify it. That is the problem. So this problem is called as, if you, I think whether you know this, class
Underfitting.
imbalance problem. Class imbalance. I think this is the term, I hope they use it. Class imbalance. Then now by this time you understood what is the best way? Stratified, right?
Stratified.
Certified.
Stratified. Now you will understand. Now if you revisit any of the Python files, if you are having C random stratified, means this should come to your mind. So what is meant by the stratified? What is that they are doing? What is meaning of this? Right. This is there are many purposes, sampling, etc., but those are mostly into business MBA kind of discussion. For us, when we work with data, is mostly random sampling and stratified. One more is there. One more is there, right? But it is too early. But still, I will try to confuse you. There is something called as k-fold cross validation. I hope maybe this is too early for to discuss this. K-fold cross validation. When you had a classifier, any kind of classification algorithm, to validate it, training, testing, etc. One more concept is there where they go for k-fold cross validation, where k is number, how many samples that you want. Suppose if you put k equal to 10, what it do is now the population. So dividing this population into 10 samples. 1, 2, 3, 4, 6, 7. So 10 samples. So randomly maybe 1,000 records and then equally something like this. Then what they do is, so we'll try in this sample, we'll take this sample, we train the model. and test on the rest. Then see how it performs. Next, what we do is take second one, train on the second one, and test on the rest, see the performance. So take only this third part, train with this data, test on the second part. So this is what is called as k-fold cross validation. So why I am saying this is, even though it is a topic later. So here there is another case where we use sampling, right? So here from the population, we have to have 10 samples. That is another case. Okay, this is the overall understanding. Why, what is sampling? Why we need sampling? So where we use sampling when we work with data. One is the dividing as a part of having algorithms, we divide the data into two parts. One is training and testing. That is where we use random sampling. So whenever we find there is a class imbalance, that is where we go for another kind of sampling, that is stratified sampling. Third discussion is there is something called as a k-fold cross validation, where if k equal to 5, then we divide the population into 5 samples. That is where we use the random sampling. Okay, so these are the 3 instances where we are going to use sampling. Okay. Yes, maybe it is too early, but I'll introduce the term. But sometimes some faculties may miss it, but as a statistics faculty, I'll try to do it, introduce the term. Now, from this is the population. From this 70%, this is the sample one. This is for training. So from this sample 2, this is for testing or validation, whatever the term we use, where 70, 30, maybe that rule what we are having. Now, suppose 1,000 records are there. Right? Then what we expect is 700 goes here, 300 goes here, right? Is it?
Yes.
But actually, when you implement, it won't go like this. So randomly it goes, right? There's now not that strictly divided. No, so these 700 you go to training, I'll go to testing. No, nothing like that actually. So randomly it happens, right? When you implement it. So this again, it may come here, it may go here, like this. It happens actually. It's not like what our understanding 700 here, 300 here, like no. So randomly it goes here if we go for iterations. Then it is observed that when we go for iterations and train it several times, test it several times, when you do it any number of times, there is some percentage of data around some, I couldn't remember exact 20 or percent of the data, which are too lazy data. This is a term which I am using. Lazy data means
It won't
lazy
go
data.
anywhere.
Anywhere.
It won't go anywhere.
No, I don't want to go anywhere. Why should I go there? 20% or at any point of they won't go. They will. Who will go there? I will sit here.
It's
So-
like a loss. It's like a loss.
Not loss. No, actually, sometimes you can see negative out of positive, positive out of negative. Actually, these guys are very important for us later. This data we can use for validation testing. If you want, still you are having any doubt on your model, its performance, you want to test it again, right? That is where this data is useful. This is called as OOB, out of box. It's called as OOB score, something like that they use. This is interesting actually. Keep it. So sometimes it is very helpful. Training is over, testing is over. Still, I am having doubt whether this model is good or not. I still am doubtful. Then you can jump into this 20% data, which is a lazy data. Lazy means it never into any of the phases. You come on now. So let us see how the model works around. This is called as OOB. So keep this term, check with when the discussion happens whether this comes or not. Otherwise, sometimes it is useful when we implement it. Okay, good. Now let us jump into the next discussion. Some terms we use. I hope now is clear. So by this time we understood something called as a population, sample, and the process is called as sampling. And whatever the statistical terms which we use with respect to population, generally we call them as parameters. Whatever the term that we use for the sample, we call them a statistic. For example, mean of the population. Generally, we denote by mu. This is a parameter. Now, if I use mean of the sample, generally we denote by X bar, which is called as statistics. Anything, mean of or variance of the population, that's a parameter. Variance of the statistic, that is called as statistics. Some terms we use, that is, one is parameter, other one is statistic. There's some terminology, nothing more than that. The interesting part is, I hope you will go through all this English, right? The same, most of the things we discussed. Why this, why not this? These are all some general techniques. For us, this is something which is important. This is what. Then purposive, judgment, convenience, quota, snowball, these are all not relevant for us. This is already what we discussed. Next is. Is it actually? So here, generally, if you see, we want, our idea is we want to understand the population, right? Our idea is understanding the population. Now, what we have been discussing, take a sample. Right? Now, do you think just by taking a sample, we would be able to understand the population completely?
No.
Right?
We'll have to
So,
adjust or do some conversion or transformation.
and a simple sense, doing samples, right? Sample 1, sample 2, then we observe how the sample distribution happens. Then based on the sample distribution, we can understand how the population distribution happens, right? That means what I mean to say is some slides. So here we are having population. Some now here what we do, we select sample 1, sample 2, need not be same size, different sizes also we can sample 3 and so on. So now every sample will have a mean, right? We'll have a mean of this and we'll have variance of it. Mean of this, variance of this, like this we have. Now, if we observe this mean 1, mean 2, mean 3, mean 4, then based on this, it's very easy for us to understand the population distribution. Means not that only one sample helps us to understand, doing the sampling distribution helps us to understand the population is the idea. That is where we introduce another random variable X bar which is related to distribution of means. That is the idea here. Okay. Now,
Isn't X bar for the mean of the sample?
yeah, so instead of mean of this, distribution of means of the sample. So
Achha,
that means,
distribution of means of the
Ah.
sample.
yeah, mean 1, mean 2, mean 3, like, right? These are numbers. Now let us have one random variable associated with it.
So what we do is we bifurcate the population into multiple samples.
Hmm.
Then we calculate the mean of each sample, and then we distribute those means.
We observe, that is nothing but we
We
observe how
we
the
ob- we
samples
observe
are
the mean.
distributed. Yeah.
Okay,
That is-
we see how the samples are distributed. So
Yeah.
that is the X bar.
Yes, yeah, you're right. That is what it calls sampling distribution of mean X bar. Right? That is what. So I hope this is clear. Now, another and very interesting, very useful thing for us is, I'll skip all those things. Let us come.
Sir,
Now,
in that
just
previous section, one doubt is this mean that we take. This is
Ah.
only if the data, if it is numeric data type or something of that sort, right? What if it is, let's
Categorical
say,
data.
a categorical data? Exactly. Thank you.
convert into numericals.
Okay.
I hope whether I think this, I didn't want to make now. Suppose in a larger picture, data means what for us? As of now, data is always we think of numbers. We'll get Excel, etc. Right? But if you see, image is the data now, right? I hope.
Yes, sir. Yes.
Image is the data. Your audio file is the data. Video file is the data, right? But finally, if you put all those things into an algorithm, what is required for an algorithm? Numbers only, right?
Yes.
So you take either images, videos, audio, text. Suppose if you take the translation, like machine translation, for example, you will enter one text in English. You ask the translators to translate to German, right? This text will go to an algorithm, right? So I hope you are all experienced, right? Algorithm requires what numbers only, right?
Correct. Yeah.
So everything will be converted in terms of numbers. Whether image or your text or voice, video, anything, any data, finally, it should go into an algorithm in terms of numbers, right?
Okay.
I hope I answered your question partially.
Yes, sir. Yeah.
You might have seen, I think, maybe in machine learning, now you are having a data X1, X2, X3, and here Y. Maybe it's a feedback kind of thing. Some inputs you are giving values here, satisfactory.
The encoding
Good.
techniques, you mean?
So we'll convert this into numbers by using some techniques, embeddings.
Okay.
It may be in the symbols at the beginning stage, we call it as encoders, encoding techniques.
One hot encoding, I think.
Yeah, one had encoders. It is simple to begin with. When you go into images, when you go into text and blah blah, there we'll talk about embeddings. So partially I answered your question, I think.
It's clear, sir. Thank you.
But sir, for categorical, for this kind of data, there is no probably relation between the two data sets, right? I mean, two datas, right? It's just to identify that this is probably a cat and this is probably a dog, right? So how can we really take a mean out of a sample of all this?
That's a brilliant question.
My discussion is, my requirement is you give numbers, I'll give the mean and all those things. Right?
Okay.
It is your headache.
Okay, but ideally, okay.
I hope I answered your question. You are looking for cat or dog, doesn't makes anything for me. You want me, give me a data. Right?
That is our headache, sir.
Okay,
Yeah,
I got it.
our
Okay,
headache.
okay.
Even I am there. Just to make things lighter, I am using this. Image you will convert into numbers. I think those who work with image processing kind of thing will convert them into pixels and do something, right?
Right.
In case of images, we'll convert them into pixels by using grayscale images, RGB, not RGB. RGB. Okay.
Right, sir.
Now the interesting here thing is, if you see this, what is your understanding? I won't comment on this. Just observe this. What is your comment on this?
Based on the sample size, the shape of
More
the
sample
distribution
size,
can
yeah, more sample size, it will be normally distributed.
It reaches or it transforms to normal distribution as the sample size increases.
That's why you see you may have different rivers. Finally, all the rivers goes into.
See,
That's why I've been telling normal distribution is very important for us, right? That's why we have been telling many times from the beginning, normal distribution, Gaussian distribution, very important, very important for us. Like you can, this slide justifies it, right? So now if you see actually, the originally population is exponential. Right? Originally population is exponential. Now, just like what I mentioned, take samples of size 2 and observe its distribution. It follows like this: n equal to 5, n equal to increase, n equal to 30. If you see what happened. So here actually is the uniform, very disciplined. Actually, it is uniform is very constant kind of thing. Even then, if you do with sample size 2, sample size 5, sample size 30. So this is U shape, how it. Then normally anyhow normal. So that's why I hope this makes very important slide. Many times we talk about the Gaussian distribution, right? Why Gaussian distribution? This is the reason. Have you done naive classifier in your machine learning? Not yet.
Not yet.
Because if you are done, maybe if you've done any assignment in the implementation, I think you know about naive, right? But you can see GNB is used in Python. Most of the times, GNB, nothing but naive base, but Gaussian naive base. I don't know whether you got a doubt. Maybe you are it. Otherwise, you will. Who told you to add this Gaussian? Right?
Just took a wild guess.
Not guess. This is actually this slides. I think this slide just was right. Where whatever the distribution it follows, mostly it is Gaussian. Finally, it goes to C. That C is Gaussian distribution. Okay, I hope. Now I think you can. Maybe you can ask your friends or like, why this GNB? Why not BNB? Binomial, right? Binomial or everything ends at Gaussian. The justification for this, you can see this. You can see this slide, n equal to 2, n equal to 20. This is discrete, right? Actually, discrete with n equal to 2, n equal to 10, n equal to 5, n equal to 20, n equal to 30. You see the last one, what kind of distribution it is following? Last one.
normal bell curve.
Normal, right? Actually, it is discrete, right? It is maybe binomial kind of thing, but finally, when it reaches the n equal to 30 and then onwards, it becomes Gaussian distribution or normal distribution. I think these are all, I think, based on, if you the discussion is clear, then you just have a look like this. Some examples, I took different example. So this is a very important slide, actually. Now, next, very beautiful thing is central limit. The most of the times interview question is this: what is central limit theorem? Why we use it? Why we are using this? All those things can be answered with central limit theorem. Just have a look and let me know what is your understanding here.
Sir, I think this is something which we saw in that earlier important slide which you mentioned.
Yes.
So it says that regardless of the initial size of the sample, if we reach sufficiently large sample size, it will reach a normal distribution.
Perfect. At least there
That-
we had something, right? Actually, some name, exponential, uniform. Even if it is not there, even if
Ultimately,
it
it
is
will
not
reach.
there, yeah, that's why whenever we use normal distribution, why? What? Who told you to? Central limit theorem permitted me to use normal distribution. That's it. I hope you answered that. That's why this is a very important theorem, which enables us to use normal distribution wherever the sample size becomes large, that is greater than or equal to 30. I hope clear, right? Very important central limit theorem. You should not say that I don't know about. You need to know what is central limit theorem. What is that? It facilitates us. Very simple. Central limit theorem facilitates us to use Gaussian distribution, normal distribution, like anything with one condition. What is that condition? Sample
And
size
should
is
be greater than 30.
and forget
Some-
about what is its original distribution. Doesn't matter for us. So that is the advantage with central.
So this is like converting any distribution to a normal distribution so as to for effective calculation and
Not only that, it is actually is we observed with this, right? Not only a comment. Now, if you see this is observation, right? If you can check it, take any distribution, increase the sample size. Once it reaches 30, if you see 5 onwards, slowly it is moving towards. Once it reaches 30, no one can stop it. It will be like normal distribution. That is what is justified by the central limit theorem. This is not like our, okay, let us know. It is giving that permission for us to. Okay, good.
Sir, can you go back to the central limit theorem? So it says that in case the initially it started, if it is normally distributed, I understood the point. If it is exponential uniform V shape, ultimately for n equal to greater than equal to 30, it will reach into normal.
Yes,
So
that is what is.
that is so. But the third point says that if it is initially normal, then mu of x bar should be equal to mu of. What can you explain the third point from mathematical
Yeah,
expectation?
yeah. This is a very simple. Actually, that is the next topic. Here, we define a random variable x bar, right?
Mm-hmm.
X bar is nothing but distribution of sample, something like that. Now, for this random variable, we can find mean. For this random variable, we can find sigma x bar, that is standard. These two are related to this random variable x bar, which we introduced, sampling distribution of mean, right? Now, this says this equal to mean of the population. And this is equal to this sigma by root n, where sigma is standard deviation of the population and is sample size. That
And
is
this
right.
is true. This is true for normal distributions.
Not normal, irrespective of the distributions.
When n is greater than equal to 30, this is true for any distribution.
Yeah, that is true. That is true. When actually
Okay.
in the regular BTech classes, we'll take a numerical example, draw the samples, find it, we'll show it actually. Not required for us. In a BTech class, we'll take that examples. One population, sample size is 2, write all possible samples, find mean of each sample, then find mean of that means, then we show it actually, but not required.
So regardless of the initial population distribution, if sample size is greater than equal to 30, the first thing is it will become a normal distribution, and the second thing is these two theorem, these two
Yes.
equations are applied,
Yes,
applicable.
yes.
Okay.
This is what we are going to use when we go
ಅಲ್ಲಿ
for
ಕುಲ
problem
ಅದನ್ನ ಕಿದಕ್
solves.
ಕಾಯ್ತವನೆ ಹಾರ್ಟ್ ಇದನ್ನ
So maybe we'll stop. We'll continue with this very nice actually. Sunday evening joining, having class with you and spending time. Nice. We'll continue
class
in
on
the
the
next
road.
class.
I think, sir, one of us are on. No worries. Thank you.
Maybe we'll continue with the next class. I think we have covered enough. I hope we can stop with this, and next session we'll cover some of the things. I'll check with the concerned for the syllabus. Accordingly, I will tune. If it is not covered, we'll skip it for post meet. Next session, we'll spend at least some time on the mid-semester related. I think we'll stop.
Yeah, sir, we
Okay,
can
sir.
stop now. It will
No,
take
very
some time
happy
for
to-
us also, yeah.
Yeah,
Digest.
very nice. Very nice. Yeah, very nice for the discussion.
Sure,
Now,
sir.
one
Thank
thing
you.
what I do is maybe today or tomorrow, I think we had all the PPT skill now. I'll fine tune them and make one PPT and share it with you. Because lots of theory, unnecessary discussions are there, right? Suppose if you see this PPT, when you prepare for examination, these are all some informations only, right? These are not that much required, right?
Thank you, sir. That will be highly appreciated.
Because
Thank you.
sometimes I'm using it again and again, right? But this
That would
PPT
be
I'm using
amazing.
in the next time. You may have a confusing, maybe just by maybe tomorrow I'll share all 8 PPTs together and I will fine tune and share it so that you will have concise PPTs.
It will have problems, right?
Yes. I'll remove unnecessary theory kind of thing, repetitions. That's it. Right?
Sure.
So that you will
Thank
not
you,
have
sir.
any
Thank
confusion,
you.
right? And you won't
Thank you, sir.
feel a heart attack like a very session consisting of 80 slides, 80 into 8, 640 slides. Wow, very difficult, right? So that
Right,
now
sir.
640 becomes maybe max 200. Right? Okay, I'll do it.
Thank you, sir. Yeah.
Sir,
sir.
also any sample question paper if you.
Already, I think already uploaded. I think already available now. But someone
Okay.
justified also. I think mentioned earlier.
Okay, then sorry, maybe I didn't check it. Yeah.
Yeah. Okay. Meanwhile, my request is just don't wait for me. Like, if you find time, just try to refresh from the beginning, so that next session you can come with doubts. So can you repeat this topic, something like that? So that don't push everything to the next session where you will reach the examination week, right? You will be under tense. Okay. Because why I'm repeatedly saying this is the first semester, no? After many years you have been going for examination, you'll have some kind of tension. That's why I want to help you in handling the tension. Right? Second semester, then you will understand. So no need to. Thank you.
Thank you very much,
So
sir.
next session,
So
can we
Thank you, sir.
do it
Sir,
for
I have one
clearing the
small
doubts?
doubt. Okay, please continue.
Yes, sir.
Actually, yes, sir. I have a small doubt regarding the standard normal distribution. In the last sessions, I mean, we are solving one problem. Could you please go there?
It means that PPT not available with me.
Mm. Yes,
Yesterday,
that problem. I mean, the next problem.
this is,
Not this one. I mean, you just demonstrated like
I think
not this.
yesterday session means that PPT is not with me now as of now.
No. This PPT only.
This PPT.
Today's
I think
problem.
he's referring to example 17 or 18.
No, it is not there actually.
Yes.
Not there. 17.
No,
This
you go. Yeah, this one or
This
the
one?
next one. I think.
No, another one is there. Just a minute. I'm telling you that number.
This is just applicability of approximation is these two problems. NP and NQ.
Yes,
calculation.
example number 19, sir.
Yeah.
So in the example 19, like we are getting that value is minus 1.40. So how we are reading the value of the probability 0.8 from that
Fine.
table. Could you please explain one?
Yeah. Now, one thing is the minus is there. If you are having other table, directly you can copy. Whenever f of minus, better write this as f of 1.40.
Okay.
Is a property. Otherwise, if you are having both tables, you can directly copy from it.
Okay.
Now just here Z equal to 1.40. Just
Yes.
go back to the table where it is.
I think it was previous.
1.40.
Yeah, this one.
Very simple. You see this 1.4. This is 1.404142 like this. This we pick. That's it.
Okay.
1 minus.
This is
Okay.
hope
1 minus 0.91.
9192. Yeah.
Okay. So
I
is
hope
it coming?
Don't forget about the values. Maybe
Okay.
some minor difference will be there because based on the tables that they use. This is how
Okay.
we do it.
Those minor differences. Okay, sir. From the exam point of view.
Yes.
Okay.
Only the second digit, second, third digit after decimal, you will have some difference otherwise.
Yes, sir.
Okay.
Thank you.
Okay, thank you.
Yeah. Sir, one question if you have time.
Yes. I'm
How
always
this
I'm having
how
time comparing with you guys.
while doing assignment at least I am facing we are making a lot of mistakes in case of numericals while reaching the absolute answer. How this exam papers are evaluated? It is to the final paper or correct formulation is there? How it will be?
The one maybe if it is a completely different answer, if combinations are correct, then they will reject maybe 0.25, 0.5, something like this, not more than that. Not like if everything is correct, full marks, otherwise, no, nothing like that.
Okay.
Sometimes even they ignore even some minor errors are there, not a problem.
So we need to reach the decimals, or we can just put the 5 by probability in
Anything is fine, not a problem.
anything. Okay.
Anything.
So they won't cancel the entire answer if the final solution is wrong. They will
if
reward mark.
if they do it, then you can raise the request, evaluation request, because answer key they share after the exam, after evaluation. Always there is a chance for you to challenge it.
So it will be stepwise marking. Yeah.
Yes.
Okay. We will be given for steps. We will give given marks for steps.
Yes.
Okay.
That's why you answer key they give generally the split up to this you will get this half mark, 1 mark like this. That generally they will mention that also to avoid any confusion among the students. Based on that you can raise the request. Okay.
Okay.
Thank you.
Thank you.
Nice for your time. Nice. Thank you.
Thank you, sir. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.